Hi guys, so today let's pick up another paper. It's called Visual Jenga by Anand, Bhattad, Konpat, Preechakul and Alexei, Efros. This is one of the papers I went and saw live in NeurIPS 2025 and I saw the poster of it. It's quite an unique approach to understanding spatial environment and dependencies of different objects in a frame. Usually most of the applications in computer vision, they rely on just the image and the environment on a face value. We truly don't understand the physical dependencies in between objects in a frame, and this kind of training is very important to eventually go towards robotic applications where we have to interact with the real world environment. So having the model understand the physical dependencies between objects is critical for robotic application and for any advanced applications in computer vision. So let's pick up this paper. Of course, firstly, this paper draws inspiration from the game Jenga, where we just have to stack different blocks and we have to maintain tower stability while removing each block. And this is our task as well. Suppose we have this image of multiple bowls stacked on each other. We have to remove each bowl with every image serially until only the background is remaining. And this is exactly what we're going to be working with. And like I gave you the introduction to this, we just have to understand the physical dependencies. Now, the entire paper has a very clear pipeline in which we mostly are using pre-trained models and pre-trained approaches. We just have defined a very clear pipeline for it. So let's get to it. Firstly, this is the concept of counterfactual inpainting. Counterfactual inpainting refers to replacing an object in a frame by different objects as if it was not even there. For example, we have this image of a cat on a table. We can replace that cat with many different objects, or we can replace the table itself by many different types of tables. In each kind of inpainting instance, we are referring that the previous object that is being removed was never even there. And we're going to have this entire flow discussed over time, but basically how we're working with it in this case is on the basis of conditional probabilities of counterfactual images. Counterfactual, in a sense, these kind of probabilities will let us know what is the probability that the scene will stay stable if we remove this object or not. And that's how we are working with it. Now, till this point in the paper, we are just referring to related work. We're going to work on qualitative 3D scene understanding that has happened beforehand. It basically refers to the layer-wise understanding of the scene, and then the counterfactual spatial reasoning. And of course, next is the asymmetric relationships in real-world images. For an example, if we often search or Google search an image of a cup, the cup will never be without a table. But if we just search for a table in Google, there will be many instances where the cup may not even be present. So that shows that there's an internal understanding between the cup and the table that it always has to be there for the cup. And this is the kind of thing we're actually working towards, where we understand again the physical support relations. And let's get to the visual Jenga task in itself. My bad. Yeah. We need to understand and evaluate scene understanding capabilities beyond passive visual observation. Given a single input image, an algorithm needs to simulate an action on the scene by generating a sequence of images where it removes one object at a time until only the background remains, while maintaining scene coherency and stability. That is our only task in this entire pipeline. Now again, let's discuss the dependency on conditional probabilities. We all know probability, and we can see A by B in this case is very small and B by A is very large. In the case of the cup and the table as well, we can refer to it in the same way, like in this case. And this is how we're going to represent different relationships between a pairwise counterfactual relationship. That's why we're gonna take everything as a pairwise dependency, and we're gonna evaluate everything on the basis of that. As you can see over here as well. Yes. Let's move forward and actually get to the crux and the entire pipeline. Again, counterfactual Inpainting method. Now, when we are considering only a pairwise relationship, we only will take the A and the B and then the rest. The rest denotes the remainder of the scene, and this is the only denotion you should actually refer to, and that is how we're just representing data. Our pipeline, this is something that the paper discusses. We'll get to this image in itself soon, but first we're going to learn the full-on step-by-step understanding as well. So firstly, we obtain the image, the object mask. Of course, we need to have that Inpainting model running, and for having that run accurately, you need to mask and mark each object in the scene very carefully. So of course, we're going to use object coordinates first using Molmo. What Molmo does is it marks each object in the scene with just a dot or like a pointer where each object exists. And then we use SAM2 to have a segmentation map for every object. It does not define it by giving it any labels, we just create a segmentation between objects. Now, once we're done with that, then we're going to get on to the second part, which is obtaining the conditional probability. Yes. As we can see over here as well, I also explained above as well. This is quite similarly where we just have to tell the relationship between two, like a pair of objects, of how they depend on each other. And we are also going to use n Inpaintings. So in this case, the number of images that we are creating, like I told you, we are replacing every object with a different one as if it was not even there at first. So we have to create n Inpaintings to have it evaluated correctly. And then we're going to use clip and dynamic representations to actually figure out the loss and everything. Clip and dynamic is essentially two different types of representations. They both refer to understanding the scene better. One understands the semantics of what all should be in a scene if we are talking about a cat and a table and a plant, for example. They all understand the scene semantics, whereas the other understands the structural integrity of the scene. That how will the cat stay in the air without the table? So those kind of physics-based constraints is understood by Dino. So we're going to use both of them to understand the scene much better. Once we have those scores aligned, we're going to remove the one which has the highest diversity score. And that's how we're going to, run the entire thing again and again by removing the highest diversity score object in each instance. Let's cover this image again. Firstly, we have the input image, then we put dots on them or mark them using Molmo. Then we use SAM to have each object segmented. Then we're going to do the counterfactual Inpainting, and then we're going to remove it using Firefly. And that's it. That's all we're going to do, and it helps us understand the system much better. For evaluation, the authors have figured out two types of evaluations. One is the NYU version 2 dataset, which has a less amount of data, the less amount of test images, which is comparatively simpler, whereas the hard pass, which has much more complex object dependencies like stacked objects or hanging or leaning objects. For example, let's cover this. As we can see in each instance, we are removing the object automatically which has the highest diversity, and you can see how it trails off over time, and we are removing each and everything in the scene. Yes. We can see the same over here as well. As I said, using the hard pass dataset, we have a much more messy desk, a messy room, or stacked objects. We can see the metrics and how it worked on as well, the NYU version 2 and the hard pass pairs, everything. This was the first instance of testing where we use these curated datasets. But in this case, we're just referring to everything on the basis of pairwise object ordering. Like I said, just understanding the pairwise relationships. Next is the full scene decomposition, where we just start from the full image and then we slowly, progressively remove everything until we only have the background. And this is something we test on again. Again, we're going to use the hard pass data set because it is much more tougher to understand for the system itself. And these are the answers, sorry, the accuracies. And thirdly is the comparison to simple heuristics. Suppose we give it a simple simple task to remove the objects top to bottom, small to large, and front to back. And that's how we're going to test it again. In all of these three cases, the results were much worse. In the case of the best heuristic approach, small to large achieves only 43% success rate, while front to back performs particularly poorly. So these were like the results. Again, we're going to have the ablation studies as well, that what depends best for the model or the pipeline. We're going to have clip and dyno both for the best diversity score, of course, and the effect of the number of in-painting samples. After n equals to 8, we don't have many better results. So that's why this paper has usually used n equals to 16 as default. And once we've covered all this, let's get to the final section of the paper. Now, in many cases, the shortcomings of this entire pipeline is, even though we understand the relationships between pairs of objects, we don't really keep in mind the exact physics behind it. And that is something that people have to work next towards, because understanding on the basis of probabilities only allows us to remove the objects in the sequence in which it is the most favorable for the system to understand. But humans, on the other hand, have a much more different approach to everything. Suppose I have this mug which has a pen and a highlighter in it. Maybe the system itself removes the pen first, then it removes the highlighter, and then removes the mug itself. But a human itself, if it has to remove something, it can also first remove the highlighter and then the pen, or it could actually remove both of them together, like having the understanding that you can remove both of them without actually causing any harm to the environment or messing with any sort of physics. So this is something that you have to understand, and the model has to understand over time, is this like understanding of the physics of the objects involved in the scene itself. So once we're done with that, we're going to discuss the failure cases as well. Lastly, of course, every pipeline has its own issue. So like I said, it only depends on the basis of the physical reasoning. That is the only thing that it lacks, because currently we are solely relying on the statistical co-occurrences. And to tackle this, it can be like a good way to use video generative models as world simulators to understand how the objects will interact with each other, considering real-time events. And some of the failure cases are the failure to remove an object in the case of any heavy shadows, and in this case gloss objects, and lastly in this case screen effects, where we are incorrectly segmenting any object, so that leads to some issues. And that is about it for the entire process of this paper. I hope I got your mind steaming, and until then, thank you very much.